Tesla just dropped a bombshell that's shaking the entire EV world. An aluminum ion battery with a mind-blowing 550-mile range, faster charging, safer, and built without cobalt or lithium. This isn't hype. This is a revolution hiding in plain sight, and it changes everything. You thought you knew about electric cars. Tesla's secret weapon isn't a new vehicle. It's the heart of the future, the battery itself. Don't blink. Hit like and subscribe right now, because what's coming next will blow your mind. Batteries were supposed to be the bottleneck. Everyone said it, everyone believed it. The conversation was always about lithium, how to charge it faster, cool it to better, stretch its lifespan just a little further. That was the game. That was the race. But while the world was arguing about incremental improvements, something else was happening behind the scenes. Not in public, not in press conferences, inside a sealed soundproof lab in Austin. Texas Tesla was building something that didn't just challenge the rules, it rewrote them. It didn't start with a breakthrough. It started with a question. Why are we still fighting the same old enemy, lithium degradation, thermal runaway, and delayed discharge? What if the real problem wasn't the battery's size or even its chemistry, but the way energy moves inside it? That's where aluminum came in. Not as a replacement, but as a redefined high conductivity abundant, capable of transferring energy almost instantly without bottlenecking. At first it was theoretical, a paper here, a test cell there. But then something snapped into place. Tesla's engineers found a way to crack aluminum's biggest flaw, ion lock. Normally, aluminum ions can't release energy fast enough. But by changing the binding substrate, a proprietary carbon graphene mix laced with atomic scale induction points, they triggered what they call quantum burst discharge. The result, power on demand. No lag, no fade, no chemical choke points. It was like going from dial-up to fiber optic, but for battery discharge. And that changed everything, because now the limiting factor wasn't how long your car could drive. It was how hard it could launch. Suddenly EVs weren't about endurance. They were about raw, unfiltered power. Super capacitor level output with the storage density of a full pack. And Tesla had it working, not on a prototype bench, but in full-scale modules, hidden under test mules, running laps on closed tracks, while everyone else was still chasing lithium shadow. Inside Tesla's high voltage testing lab, the numbers were never meant to leak, but they did. What they showed wasn't just progress, it was a leap. 7,000 watts per kilogram, a figure 5 times greater than Tesla's own 4,680 lithium-ion cells. That's not a battery anymore. That's a contained explosion, tamed and delivered through software, tuned pulses fast enough to rival direct fuel injection, and yet cool, stable, repeatable. The new aluminum ion cells didn't balloon under stress. They didn't need cryogenic cooling. In fact, they performed better. This is come to perform better as the heat climbed. Most lithium cells degrade above 40 degrees Celsius. By 60 degrees Celsius, they're in thermal runaway danger. These new Tesla cells, they're most efficient at 85 degrees Celsius. Where lithium would die, aluminum thrives. That's because the chemical transfer doesn't rely on thermal activation. It relies on pulse resonance, triggered by a new kind of signal controller inside the battery management system. Tesla calls it QBC, quantum burst control. It doesn't just regulate power, it shapes it. Even after 10,000 full cycles, lab reports showed no measurable drop in output, not 1%. Same torque, same launch, same range. That's over 25 years of daily charging with zero fade. And for Tesla, that wasn't a brag. It was a requirement. because the vehicle says this battery wasn't a luxury sedan. It wasn't a $120,000 flagship. It was something else entirely. Tesla didn't just build a new battery. They built a new class of vehicle around it, something the industry still refuses to believe is real. Internally, it's referred to as Project Redwood. Publicly, it'll be known as the Model 2. Price under $16,000, range 550 miles. Charge time 5 minutes. That's not marketing. That's what's already been demonstrated at Tesla's closed-door testing events. 5 minutes from 0 to 100% on a level 4 aluminum capable charger using quantum burst modulation. This isn't a theoretical leap, it's a practical one, and it's scalable. When journalists were quietly invited to ride in the first pre-production Model 2, they weren't told what powered it, but they noticed something. This wasn't just a cheap EV. This thing launched like a beast. 0 to 100 kilometers per hour in 3.2 seconds. Silent, violent, relentless, and not just once, over and over again with no thermal throttling, no lag, no drop-off. Porsche Taycan's overheated after a few launches. BMW's i4 throttled at 50 degrees Celsius. The aluminum ion Tesla, it just kept punching. And that's when the realization hit. This wasn't Tesla catching up, it was everyone else falling behind. Because while legacy automakers are still trying to push $60,000 EVs with 30 minute charge times and fragile battery chemistries, Tesla is preparing to flood the market with a $15,000 electric missile that never fades, never overheats, and charges before you can finish a cup of coffee. The shock wasn't that Tesla built a better battery. The shock was that they made it cheap, not someday. Now this wasn't a concept, it was already rolling off a limited production line. Modular, simplified, vertically integrated. Every cell manufactured in-house using materials 10 times more abundant than lithium. No cobalt, no nickel, no supplier, chain hostage points. Just pure domestic built speed wrapped in the silhouette of the most accessible EV in history. No one was ready, not for what came next. Just because while the world obsessed over lithium, cobalt, and conflict minerals buried in war-torn soil, Tesla looked the other way at an element so overlooked, so ordinary it was practically invisible. Not because it lacked power, but because it was everywhere, too common to be revolutionary. Until now. Aluminum's the third most abundant element on Earth, light, strong, and endlessly recyclable. For decades, scientists mocked its potential as battery material. Too unstable, too reactive, too primitive. But Tesla's latest chemistry hack flipped that script by using a crystalline structure embedded with graphene-like lattice modifiers. The aluminum core didn't degrade under use. It got stronger. The more it charged, the tighter the structure locked. Not in bomb punch, decay activation. This new cell didn't just remove the need for lithium. It erased cobalt, no. Nickel, no rare earths, no dependence on China's mines or Congo's human cost. Just raw scalable American aluminum, refined with AI asshole optimized iron layers. That self-organized under current load. But the truly disruptive twist heat, the one thing that kills lithium awakens aluminum. The hotter the battery got, the more conductive its internal channels became. No fire risk, no bloating, just raw power efficiency. Accelerated, not suppressed by extreme heat. In deserts on racetracks under pressure, aluminum didn't just survive, it thrived. And with lithium supply chains now cracking under geopolitical weight, this wasn't just a technical win. It was a geopolitical dagger, a supply chain upheaval, a sovereign flex that Tesla alone seemed prepared to wield. Then came the moment no one believed. The one fear every AV skeptic clung to like gospel charging time. It was always the same debate. EVs are great, but I don't have 40 minutes to wait on a road trip. And just like that, that excuse shattered. In a closed door or investor demonstration, Tesla brought out a single Model 2 prototype stripped of flare, cloaked in black. Engineers plugged it into a standard supercharger, no experimental gear, no tricked cables, and hit the timer. What happened next wasn't a stunt, it was a benchmark reset. 5 minutes, not 50, not 35 minutes, to 80% capacity. The audience didn't applaud, they stared because the implications were seismic. No special infrastructure, no nationwide rollout, just a new cell chemistry and a hypercharge interface engineered to channel energy through nano-ruptured pathways without triggering heat spikes or degrading the anode. Those tiny channels, self-assembling through AI, predicted formation models, allowed ions to flow like liquid light, bypassing the resistance points that's traditional batteries. And more shocking, the cell didn't even get warm. No fans, no cooling coils, just raw transfer absorbed with total efficiency. In post-demo surveys, Tesla revealed the figure that silenced every boardroom skeptic. 65% of EV hesitant consumers said their number one fear was charging time. That fear is now obsolete, but it wasn't just speed, it was stamina, where lithium ions degrade, fracture, and lose capacity with every hard cycle. Tesla's aluminum ion design did the opposite. Each cycle realigned its ion layers like bone healing after stress. Even after 500,000 full discharge recharge cycles, the battery retained 100% performance. That's over a century of daily use without decline. And that wasn't theory. Tesla ran the cell under urban delivery van. Simulations, full stop braking, heat cycles from minus 10 degrees Celsius to plus 90 degrees Celsius, and rapid acceleration loops are designed to mimic towing uphill at full payload. Not once did output throttle. Not once did temperature spikes trigger shutdowns. The battery laughed at stress. Regenerative braking, too, became something else entirely. Aluminum ion superconductor pathways allowed up to 98% energy recapture. In dense urban zones, that translated to 20% more usable range, not from charging, but from braking. You didn't just stop the car, you reloaded it. Thermal throttling gone. No more. Your car is cooling. Please wait. Drivers say can push aluminum ion to the red line in desert heat under heavy load at track speed, and the power curve remains flat. No tapering, no lag, and no, you're too aggressive. Try again later. Just raw, repeatable power on demand. And unlike other so-called solid-state prototypes still stuck in labs or costing $80,000 per unit, this wasn't a concept. It was real. It was durable. It was ready. The world's most mocked element had just broken the rules of physics, and Tesla was already building the future around it. But building the future takes more than breakthroughs. It takes a new kind of battlefield. Tesla's revolution didn't just stop at chemistry. It found a home, a fortress, in a sprawling factory nestled deep in Mexico's industrial heartland. This wasn't just another factory. This was Giga Mexico Tesla's first production facility built exclusively for aluminum ion battery packs. Every inch of it was optimized for speed, efficiency, and scale. Gone was the water-heavy, slow wet coating process of lithium cells. Instead, Tesla deployed dry electrode manufacturing, a game changer that eliminated billions of gallons of water waste annually and slashed production time in half. In this factory, 500,000 battery packs would roll off the line every year, occupying just a third of the footprint lithium plants require. Vertical integration met robotic precision in a dance choreographed by AI. Robots managed 98% of assembly with human workers limited to quality oversight and rapid maintenance. This wasn't just automation. It was an industrial weapon designed to outpace any competitor. And the logistics blazing fast. The first battery modules took less than 72 hours from assembly line to delivery truck. A speed that reshaped supply chain expectations and created a logistical nightmare for legacy manufacturers stuck in weeks or months of delay. The factory wasn't just producing cells, it was launching a new era of energy independence. Tesla's ambition didn't stop there. One factory alone couldn't change the world, so they planned to swarm dozens of micro-factories scattered across the globe. By 2026, 35 such units were confirmed in 12 countries. By 2027, the target was 100 micro-factories in 20 nations, each capable of producing 1 million battery packs annually. This wasn't centralization. It was a decentralized power grid of production. Each micro-factory operated as an autonomous unit, smart and responsive, guided by AI systems that optimized output based on real-time market demand. This radical shift shattered the lithium monopoly, the chokehold held by China and a handful of refining giants. Tesla's distributed network reduced transportation costs, slashed tariffs, and eliminated geopolitical bottlenecks. Energy production became local, flexible, and unstoppable. It was less factory and more a living organism, a global energy hive with Tesla at its core. But what does all this mean when you get behind the wheel? The answer: everything. The moment you press the accelerator, the power is immediate. A surge of torque that obliterates lag. No delay, no fade, no excuses. It's a raw power, pure and unfiltered, delivered with surgical precision. That instant torque rockets the Model 2 from 0 to 60 in just over 3 seconds. But unlike traditional supercars, this acceleration repeats endlessly without any thermal cool down pauses. Take it uphill with a trailer, push it into tight corners. Accelerate past traffic on the highway. The power curve remains unshaken. No degradation, no throttling, no hesitation. Ludicrous mode can be engaged lap after lap, sprint after sprint, and the battery laughs in the face of heat buildup. The car feels less like a machine and more like an extension of your own body, a rocket strapped to 4 wheels with a steering wheel. Drivers who've tested the Model 2 report an uncanny connection. The car anticipates inputs before the foot hits the pedal, adjusting energy delivery dynamically to their style and the road ahead. It's as if the vehicle is reading their mind, syncing power output in real time for optimal efficiency and thrill. This isn't just driving. It's a symphony of man and machine. This is more than a car. It's a revolution on wheels. A glimpse into the future where energy is abundant, fit, and endlessly reliable. Tesla's aluminum-ion battery isn't just a technical marvel. It's the beating heart of a new era. And the world is only just waking up to its power. But that power isn't locked inside a lab. It's rolling down streets, plugged into driveways and lighting up possibilities we never imagined. A single battery pack inside the Model 2 isn't just a powerhouse for the road, it's a powerhouse for the world, capable of delivering up to 2 megawatts of instantaneous energy. This pack can light up 200 homes, keep heavy industrial equipment humming for hours, or power entire neighborhoods during outages. Tesla isn't selling a car anymore. They're selling a mobile energy node, a portable reactor that transforms every Model 2 into a decentralized power plant. Directional charging technology turns the vehicle into more than transportation. It becomes a lifeline. Homes, trailers, even small cities can draw electricity directly from the car's battery. Imagine a future where every parked Tesla feeds energy back into the grid during peak hours, smoothing demand surges, stabilizing local networks, and empowering communities to become self-reliant. The aluminum-ion system's resilience and efficiency make this vision practical, turning every Model 2 into an integral part of a massive distributed energy web. This isn't science fiction. It's Tesla's bold blueprint for the energy revolution, where cars aren't just vehicles, but vital infrastructure. They're mobile reactors, constant power sources, and flexible energy storage units seamlessly woven into daily life. The implications ripple far beyond the streets, threatening to upend how power is generated, stored, and distributed worldwide. And for combustion engines, this is the final strike. The Model 2 is cheaper than almost every gas-powered compact car on the market, faster than many sports cars, and cleaner than even the most advanced hydrogen vehicles. When stacked against competitors like BYD's Dolphin or the Xpeng G9, it doesn't just lead, it obliterates. Under $16,000, a 5-minute recharge time, 550 miles of range, and supercar acceleration, it smashes the old logic of compromise. Fill up times at gas stations now look archaic, sitting idle next to Tesla's 5 minutes charge. Maintenance costs approach zero. Fuel expenses evaporate. The internal combustion engine's centuries-old reign crumbles under the weight of pure economics and brutal performance. This isn't hype. It's the first time electric vehicles have decisively won the race across every meaningful category. The end of combustion is no longer a question of if, it's a question of when. Beneath this shift lies a deeper seismic upheaval. The death of lithium. Tesla's aluminum-ion batteries slash costs per kilowatt from lithium's bloated $120 to an unprecedented sub $40. This cost collapse alone threatens to dismantle the entire lithium supply chain. A $10 billion annual disruption Tesla openly projects. But it's not just price, it's control. The entire battery life cycle is designed to be circular, local, and autonomous. Up to 95% of materials are recycled on-site. No sprawling mines in unstable regions, no geopolitical choke points, no dependency on a single nation or company. China's decades-long monopoly on lithium refining, over 80% of the global market, faces its most existential threat yet. Tesla's swarm of micro-factories, each pumping out millions of aluminum-ion packs worldwide, breaks the supply chains apart and scatters the power. The lithium era is ending, and Tesla's energy empire is rising from the ashes. This is no ordinary car launch. It's a declaration of independence, a shot fired in the silent war for the future of energy. The Model 2 stands not only as a vehicle, but as a symbol of innovation, defiance, and a new world order in motion. And as the dust settles on the lithium age, one question remains etched in the air. How fast will the rest of the world catch up before they're left behind?